All right. Whoa. That was scary. Okay, we're just a few handouts short. My relationship with printers today wasn't so great, apparently. So can you share with people next to you instead of us running to go get it's a good opportunity for social connection. Bonding over C++. Okay. And also the slides are online, the videos are online. I think there are resources. It's way too loud. Tolerable? Is that better, back row? Not like, okay, thank you. All right, so let's talk about a few things. MP, you're kind of in the middle of MP2 now. It's released to you. All the things that we're working on now and this week are relevant to MP2. The other thing we have going on is your first exam in the CBTF. So we noticed a lot of people missed their exams. So that's okay, as long as when you go there and say, I missed my exam, there's a slot for you, but it's rolling the dice as to the availability at the testing center. So please, if you sign up for a time, be sure to make it, because it screws up everybody if we don't. All right, let's see. What else was I going to talk about? Are there any other administrative questions? Oh, problems of the day. Problems of the day will be coming out at 4 a.m. tomorrow morning, tonight, essentially while you're sleeping. Angels will come and bring the problem of the day for tomorrow. And then we hope, as long as we keep it going, it'll be every weekday thereafter. So at 4 a.m. Monday, Tuesday, Wednesday, Thursday, Friday. And then beyond that, who knows? I mean, on weekends, and then all semester long. Oh, no. Okay, last hour, I came here last 11 o'clock, I came here, and I felt like my head was over here and my mouth was over here. I had neither brain nor ability to put words together. I'm starting to think it's not any better this hour. I don't know what it is, but I'm starting to think it's, it's still a problem. If at any point you want me to put down the microphone or give the microphone to Wade, just give me the signal, and I'm happy to do it. Right, Wade? Yeah. All right. Is that the signal? Oh, no. Okay.
I'm just asking, are we allowed to do something to Wade if you become next?
If Wade starts screwing up, you give him the signal and he gives it back to me? Yes, sure. All right, so breathe. Yes? Yeah, the problem of the day is there's always this 4 a.m. cutoff. The old one is due, the new one comes out. So, yes, 24 hours, clockwork. Any other questions? Administrative issues, we're working on grading, yeah? Problems of the day are 1/10 of a point of extra credit each one. Yep, yeah? Oh, yeah, that's a separate issue. I'd prefer to talk about that offline. Yes? So are you talking about the exam because we had Prairie Learn issues in both cases. Are you talking about the lab quiz or the exam? The lab quiz, there's no problem because we can hand grade. You wrote down your answers on the paper, right? So that's what we're going to do. We're going to grade those by hand. I don't know. So I don't know when the grading is going to, oh no. I don't know when we're going to catch up with grading. Okay, and then the other piece, see, that's my brain. There we go. All right, the other piece is the exam's going on. I already talked about it. Okay, can we work? Because I'm much, much, much more comfortable talking about C++ than I am stuff. All right, so last time you learned a bunch of stuff and I wasn't here. So it's kind of important that you fill me in on what you now know. So one of the things you learned about was kind of like your very first data structure. It should have felt to you like the first time you could imagine using C++ to store a whole bunch of data. So what was that topic? What did you learn about last time that allowed you, this is my clue, this is my physical clue, allowed you to store a whole bunch of data? What was it? Arrays, that's right. So you learned about static arrays. They live on the stack. There's a little, phonetic likeness there. You also learned about dynamic arrays, where the data associated with them lives on the heap. But you didn't really learn an explanation for why those are called dynamic arrays yet. That should feel a little bit like a misnomer because we gave you the space for it, but it doesn't feel very much like you can change it. And that will come as we go. The other thing you talked about, I'm going to give you a clue for, I think, is something that starts with a P. Do you remember what that is? Somebody raise their hand and confess what it was. Yeah, you're grinning. A grin is just as dangerous as a hand raise. Oh, problem of the day. You probably talked about that too, and it does start with P, but that's not, It's hard to penetrate my brain today, because mush. But what else did you learn on Friday? Parameter passing, good. Is that what you're going to say, Joel? Yes, very good. And there were 3 different ways that you can pass parameters. The first one is the C++ default. It is referred to very quickly as pass by value. Very good. Pass by value. The second one is really just pass by value, but it sort of gives you additional utility. And we commonly refer to it as pass by. Do you remember what it is? It also starts with a P. Pointer, good. I'm going to write it like this, though. And the third one was probably novel to almost everybody in this room, and that was pass by reference. Very good. Okay. Now, this slide this slide was the very same one that we used to talk about passing parameters from the start. But this time, in today's conversation, we're not going to talk about passing control flow to a function, but rather we're going to talk about what happens when control flow passes back from the function to the calling function via the return statement. So we're going to spend a fair amount of time talking about what happens to this value right here upon the completion of the function. Okay? Now note that whatever thing sits here, whether it's a value or a variable, has to match in type to whatever is sitting here. That's the convention of return values. We've seen it over and over we see it over and over in many different languages. Okay? All right, so here's the first new thing. We're going to talk today a little bit about the 3 different ways that you can return values in C++. The first one is, got any guesses? Return by value. Very good. Okay? Very similar. A copy is made, sort of, upon return. Or we can return by pointer, or we can return by reference. Good. Okay, and that really is the substance of the first part of our conversation today. Okay, so what happens when you pass control back? That is, what is the value of this? The way we're going to think about it is that there is like a token. Maybe you can think of it as a variable, but really it's an internal representation of the data itself. And in our discussion, I'm going to refer to it as kind of this capital T. It stands for the return token and what it means upon the return. Okay? So that value is given by whatever sits in this return spot. Now, when you return by value, you can imagine that a copy is made into that token, into that spot that holds the return value, okay? When you return a pointer by value, the same thing happens. A pointer, an address, is copied into that token value. Okay, we'll see examples in a minute. But when you return by reference, just like we saw before, that token becomes just another name for a different piece of memory, just as when you do parameter passing. All right, so let's look and see if we completely understand what's going on here. Let's look at a little tiny example. I'm going to trace this code, and it employs the green code. And the way I'm going to sort of keep track or animate the execution of the code is by drawing out the stack, the memory stack, very loosely, very abstractly as we process it, okay? So just like last time, we have this struct student at our disposal, and it has 3 little pieces of data associated with it. So when I declare a student C, it's like C gets set up on the stack somewhere, top of the stack, wherever the next spot is. And when I initialize pointer D, D gets set up onto the stack somewhere. It's going to be a pointer, so I'm going to put a little dot there to remind myself that it needs to go somewhere. And then I'm going to initialize C, which simply means, in this case, give those 3 variables some value. 3 member variables some value. Okay? Any question about that? Is that clear? All right, and now I'm going to call print student 5C on C. All right, you learned last time that when you pass by value, a copy is made. So S is going to be set up on the stack, and somehow, that should make you curious, a copy is made of the values for C. Then I'm going to execute this code. Student W equals S. Well, where does W live? On the stack, right above S. Good. And it gets the values for S. Okay, looks a lot like S. Then we're going to mess with W, and even part of W gets changed, so W is a little bit different. And then I'm going to return the address of W through the return statement, okay, and assign that value to D. Now, first of all, do all my types work? Is this okay to return the address of W through a student pointer return value? Is that okay? Yes, perfectly fine. No problem there. Moreover, is it okay to make that assignment to D? Yes, type-wise. It's perfectly fine. Now let's look at it value-wise. When you make this return of the address of W, it is as if D points to this, right? Or that T, that token, represents that. But here's the problem. As control flow passes back from the green box to the blue box, what happens to W and S? Yeah? Yeah, look, remember, these are stack variables, right? That means the scoping mechanism is sitting there ready to help you out and get rid of your memory anytime you ask it to, which means when something goes out of scope. So that means that the second this arrow happens, the second control flow passes back to the blue, that memory is returned for use, and this memory is returned for use. You like this? Tell me about D. Nobody likes a D. What's wrong with D? Yeah, look, it points to invalid memory, right? Yeah, it points to what you have to consider to be garbage. That's right. Okay, any question about it? Is it good? Do you like this story? It's a terrible story, but you got it. All right, so describe it to me in one sentence. If I say do not ever, 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 what is it that we shouldn't do here? What should we not do? What did we do wrong? What did we do wrong? Yeah? We didn't return by reference. Shouldn't, that's really close. Yeah? Right. Or return the, when you say a pointer to, I'm going to say the memory address of. Those are the same, right? Okay, good. So do not ever return memory address of a local variable. Can I fix this like this? Instead of returning W, can I return S? Return the address of S. Would that be okay? No, same story, right? Because that's still invalid memory. Parameters, value parameters are just like local variables. All right, so do not ever return the memory address of a local variable or a parameter, value parameter. Okay. Yes? Yeah. You and I, right, together. Okay, so the question is, how do we fix this? One way of fixing it. If we decided we must return a pointer to something, if we must return a student pointer, then what we need to do is make sure that that pointer points to some memory that we control, right? That is, that return value is really just going to hand off reference to memory that's going to persist, and we know how to do that. So instead of student W gets S, we should have or could have done student pointer W equals new student. I'll tell you that that constructor exists, and then when we returned, it would just be return W. Then we're returning a pointer by value, and that pointer is going to be, that value is going to be what we capture, not the particular position. Okay, and the value will persist because it's on the heap. Any question about it? Yeah? Yes, somewhere. Okay, so here's what it looks like in memory. So now, when W gets some value, it looks like this. Yay. And D is going to point to that same value after the assignment. And this pointer right here doesn't exist anymore. Everything is good, except now we run the risk that this memory will leak. So somebody has to delete it somewhere. So usually when there's an allocator function like this, when there's a function that allocates memory, there's a paired function that you can deploy to get rid of that memory as well. They kind of come in pairs, just like new and delete do. Okay, any questions about all this? All right, let's keep going. We have a ton of stuff to do today. All right, so let's try return by reference, because that's just weird all around. I'm going to do the same thing. I'm going to set things up on the stack. This time, yeah, I'm going to draw it like this, and here's D. I'm tracing this blue code. C gets some value. I'm just making a note there so I can see it. The function is called, S is set up on the stack. The value of C is copied into the location for S. We do the same thing for W. And then in the code, we change W a little bit. Now we're ready to talk about what happens when we return W. So first of all, is the type okay, do you think? Do you think the type is okay? And the way I want you to answer this is I want you to come to a consensus with the person sitting next to you, okay? Decide with the person sitting next to you whether the type is okay or not okay. So I'm asking you, putting it right back at you. Are you ready? So the question is all about, can I return W as it is through this return type? Raise your hand if you and your partner, both of you raised, okay, this is, raise your hand if you and your partner said, no way, there's a type mismatch. Yeah, no way, there is a type mismatch. Raise them high, it's okay, we're all friends here. Oh, you guys, really? Just kidding. Yeah, so raise your hand if you think it's okay, no type mismatch. Okay, it looks like a toss-up from this end of the room. The answer is there is no type mismatch. So, even though it's counterintuitive, it looks counterintuitive, the same principle applies as pass by reference. It's used, that ampersand in that location is used as a flag to say, oh, I'm not passing by value here. Don't make any copies. Same thing in passing and in returning. Okay? So you don't have to worry about what that ampersand means in terms of a memory address. Here you should think of it as a flag. All right, now here's what that flag does. That flag essentially takes this token that I referred to here and has it refer to exactly the same place as in memory as whatever was there. So it is as if another name for W is just sitting right here. Do you like that? Is that okay? Where's W after return, by the time control passes back here, where's W? What W? I never heard of a W. There's no W. W is gone. And yet we're trying to use it on the right-hand side of this assignment statement. So one more time, when we return W by reference, it is as if we are giving another name to the memory address formerly known as W, using it on the right-hand side of this assignment statement, and that second that you return it and it's sitting there, it is invalid memory. Okay? Any question about it? All right, so the lesson is don't return a pointer or value param to local variable. Oh. I need to write upside. Local variable or value parameter there. Nor a local variable by reference. Local variable or value param by reference. Okay, I have a question for you before you ask me, because I think you might, and that is, if you can't return anything by reference, why do you have it? And my question for you is, what can you return by reference? Yeah? Yeah, you can pass a reference parameter by reference. You can return a reference parameter. About it. You can also return a reference to the current thing, or the address of the current thing, because it doesn't change. Anything that's guaranteed to exist outside the scope. All right, yes? So since W, I heard this since W is on the stack, and then I lost you for a second. So try to speak just a little bit louder. So the question is about what if W were a pointer and we had it on the heap? Then we would draw a different picture, right? Because if if W were allocated, if we allocated W, then it would be, here I'll put it in red like the previous slide, student pointer W equals new stu S, okay, and then this would be our picture, this, right? And if we return, what? Oh, if we returned this by value, oh, is this what you're asking? Does this work? No, I'll fix it. No type mismatch, because we do reference W. Does this work? I'm like trying to do this faster than, I'm trying to do this myself. But I've dereferenced W there. No, there's no copy anywhere. Oh, but then I give a name to that. You know what? I don't know the answer to this. I want to go play. Don't know. And this might be a 10-foot I don't know. This might be a, when I leave this room, I'll be able to go, yeah, I get that. But the way I'm going to go play with it is I'm going to go write a few lines of code and see what happens to the value when I return it here. I think the types are all okay. I know that this thing out here has a value, and I don't know what happens if you give this token, this token indicator to this, and then call it D. I just don't know. I'm going to go figure it out. We have that power, okay? All right, I'm not going to ask any questions. Instead, we're going to kind of switch gears. The reason I spent some time on return values like this is because these are two extremely common errors. And they hit you in weird places, right? Like, you don't know when that stack is going to be used. You might get a seg fault or you might not when you dereference D if it points to the wrong place. So these can be kind of insidious problems. All right. I want to move on for just a little bit to address another issue that you learned last time. So last time, you learned about arrays, and it means that we can be cleverer about the objects that we create. And so I want to exploit this for just a minute. So the idea now is that we take our stupid sphere class and we make it a little fancier. So we have a fancy sphere class. Now, here's what a fancy sphere class is supposed to be like. I'm going to declare a sphere, and upon declaration, I want a sphere to have the following values. I want its radius to be 1.6, its numats to be 3, and I want this to be this array. Okay? Does that surprise you a little bit? Remember that to declare an array requires a variable that is just a pointer. So this right here as it is really gives you very little clue about what you're going to use this at field for. And I'll tell you that what you're going to use it for is to give value to this array. So what we're going to do is this one is going to be red, this one is going to be crunchy, and this one is juicy. So a default sphere here is an apple. Okay? Any question about that? Now the question is, how on earth do we make that happen? Who controls what happens when we make a declaration like this? What code is executed? the constructor, right? So what we're going to do is we're going to use the constructor to make this fancier default sphere. I have the skeleton for that new constructor right up there, so let's fill it out together. Now, when I build a constructor with very many private members, I always use the data members in the class definition as a sort of checklist for building my object. So, for example, the first value that I'm going to assign is to the radius. And I'm going to do it this time through the initialization list. I'm going to say the radius is 1.6 because we said that was a good idea. For an apple, we need an apple. It's about 1.6 inches in radius, right? Like that. Is that an apple? That's a pretty big apple, actually. Okay. Then we want the number of attributes to be 3. And now I have to initialize that string pointer. I'm going to assign to it. How am I going to give it value? What is the next letter that I'm going to write? And I want you to whisper it to the person sitting next to you. The next letter that I'm going to write. And I'll remind you that this is acts as a string pointer. What did your partner say? Everybody say it at the same time. The letter. Good. New string 3. What's the giggle? No way, it was a guess? Fine. Yeah, it does. Radius? Yeah. Okay. Then, okay, now life is easy because now I've got an array. So at 0 equals red. Yay, I'm in comfortable land here. At 1 equal crunchy. At 2 equal juicy. All right, any question? Is it good? Yeah? None of it's in the initialization line. I believe that I can put that one in the initialization line if I wanted to, but not the others. Yeah? If I said num ats equal 3, yes, sure. Oh, yeah, I should have written num ats there. Yeah, yep, that's better. Sorry. It doesn't really matter because I still kind of hard-coded it because I did them one by one. It's a little bit better to have just no magic numbers, or as few as possible. Okay, anything else about this? No other questions? Yeah? The colon before the radius, because the radius in numats is the initialization line where you can initialize the private members using that alternative syntax in constructors. So in that sense, this constructor is just like the ones we did before, that we can use that space to initialize them. It's exactly the same as if I had written the radius equals 1.6 within the code block. Exactly the same. All right, any other questions about this? So we had a question. Yeah, go ahead. No, do you see any parameters here? So the question is, what is this constructor used for and how is it used? I'm saying we're all agreeing in a design discussion that a default sphere should be an apple. We decide that. The best sphere in the world is an apple. Okay? So that constructor, no matter what, is always going to make an apple. So yes, there is some hard coding in there, but it's because of a design decision. We decided that that was what a default sphere was going to be now. Okay? Does that answer it? I wasn't sure. That doesn't preclude us from doing another constructor that allows us to initialize a sphere in a different way. We can still do that. But like we could say we want an array of like 25 here if we have 25 attributes of a sphere. Okay? All right, any other questions about this? There was one thing that came up that I really want to hammer home on just a little bit. So ats is a string pointer. And ats is a string pointer, and we have this syntax. And last hour, somebody said, wait a minute, where's the dereference? Ats is a pointer. Here's how to think about this. The square bracket is the dereference. Okay, so when you read this, and this is very simple because it's only one dimension. When you read this, you go ats, the dereference of ats, and 2 steps forward in memory. Okay? That's what this means. But if you'd rather think of things in terms of an array, that's probably better actually. But in terms of the pointer, your dereference is sitting right here. Dereference ats and take 2 steps forward and write a J. That's all it is. Okay? Any question about it? Yeah? The address of the array is probably the locate. Yeah, I mean it's the value of ats, right? If you went cout ats, you get the location of A0. Yeah, and this is a case where you actually do kind of have a name for things on the heap. Okay, all right. Any other questions about this? All right, so now we've got this new fancy kind of thing, and what's fancy about it, what you couldn't do before when we talked about constructors the first time, is we had no notion of dynamic memory, and we certainly had no notion of arrays. So, this is new territory for us. All along in our discussion over the last few days, we've been kind of saying a phrase that wasn't complete enough, and it should have made you go, wait, really? What? How does that work? And that phrase was, a copy is made. So I want to revisit that for just a second in the context of this example up here first, okay? So here's what's going on here. We declare a sphere A and a sphere B, and we're going to give A value. Then we're going to pass A through the parameter to S by value. What I said before is a copy is made, but what really happens is a special constructor that you write for the system is invoked for you. That constructor is named the copy constructor. So I said a copy is made, but what is really true is the copy constructor is invoked. So, whoa, so now there's this new thing that we got to think about writing, maybe. Now, if you don't write a copy constructor, there will be one. No problem. There will be a copy constructor. You can pass parameters by value without writing a copy constructor, but what you're going to have to diagnose is whether or not the default one is good enough for you. Okay, so I want to visit another issue in the context of this same example because I think it's kind of interesting. We're also, in this example, returning by value. Now, as I said before, it's like a token is created in this space that's a copy of S. But here's the thing. When the compiler can figure it out, when the compiler can figure out the value of what T is really supposed to be, it doesn't actually make the copy. So you cannot count on the copy constructor being invoked upon that return value. It does this because copies are slow, and it's good to not have to make a copy if you don't have to. So this is an optimization that the compiler will do for you when it can. Now, can you as a programmer predict when it's going to happen? Well, maybe for today in this particular compiler, but it varies by compiler and it's ever changing. So you can't count on any particular behavior. What you should think in your mind, though, is that that return value, that token, is a copy of whatever is returned. You can think of it that way. It's safe to do so. What you can't necessarily guarantee is that it was your copy constructor that made the copy. You can believe that it was a good copy, but you can't know that your copy constructor was the one who made it happen. Okay, I want to talk about another way of using the copy constructor. And this one won't surprise you at all. So suppose we have sphere A, and we want sphere B to be a copy of A. That's how you do it. So this is pretty much as close as we ever come to calling a constructor, right? It even looks a little bit like a function call. Okay, all it's saying is make B a copy of A. Moreover, you already saw me do this next example. If I say sphere pointer B equals new sphere A, the copy constructor gets called there too. Okay? Any question about all of that? So let's go write a copy constructor. There's the declaration. That's what it looks like. So that's the function that we're going to be writing. We're going to write sphere with a parameter whose name is orig, and it's orig that we're going to be making a copy of. So orig is the name of the thing that already exists. Okay. Before we do that, though, see, I'm telling you, not a good day. Before we do that, I want to talk for a second about what happens by default. That is, if you use the default copy constructor, what is given to you. Let's suppose that I have initialized A, 1.63 red, juicy, crunchy, and I want to make a copy of it in a variable whose name is B. Here's what will happen for you by default. It's awesome. Doubles know how to copy themselves, and so a perfect copy will be made of the radius. Okay? Integers know how to copy themselves, and so a perfect copy of 3 will be made in the space for numads. Okay? Pointers know how to copy themselves. They're kind of like integers anyway. And so a perfect copy of that pointer will be made in the respective space for B's ats. Yay! Do you like it? This is the default. This is the default behavior. Okay? So by default, no memory is reinitialized for you. No authentic assignment is made of anything on the heap. Pointers are just like integers. They get copied. Okay, any questions about it? I think you should have a question. I think there's an interesting question here. And it is, what if you had string name? So there's another field here. Its name is name, apple. Question is, do strings know how to copy themselves? What do you think? Do strings know how to copy themselves? What do you think? You have to say it really loud. You don't think they do? String's not a primitive. Oh, okay. It would be a huge bummer if strings don't know how to copy themselves. So, yeah? Very good. Right, think about this. Strings are just an object, right? In fact, you know, a stupid string probably doesn't look very much different than this class right here. A string is just a class. And the way it knows how to make a copy of itself is via its copy constructor. That's right. So when I say this phrase, knows how to copy itself, for non-primitive types, what I really mean is it has a valid copy constructor, okay? And that's what we're building. That's what we're building right here for the sphere class. Okay, I want to write this really, really quickly. I have no idea what time it is. No, 48. Oh, it's okay. Let's write it really quickly and we'll be good. Okay, so all you have to do is think about how to build one of these things. I'm going to use the initialization list. You should see if you can beat me. It's colon here. The radius becomes Orig's radius. Num_ats, becomes Orig's num_ats. And then Orig's values can't be copied directly. We need to create this space. So now the code looks like it did in the original constructor. So ats equal new string num_ats. And then this time, it's kind of nice, for int I equals 0, I less than num_ats, I plus plus, ats sub I equal orig dot ats sub I. We copy the values over. Okay, I think you should, there's one fascinating question here. One question that feels like this has to be wrong. Yeah? Yes. That was it. Wait 1 minute. We're using Orig's private members, right? Why is that okay? The answer is because, I'm going to put it in red so you can see it. Orig is a sphere, and we're defining a sphere class member function. So because they are of the same type, the sphere class member function has access to Orig's private members. I don't need to use the getter functions here. Okay? I can't even tell you how much I was hoping you were asking exactly that question. All right, that's it. Hi.
Hello. Okay.
exist. This little box is a over the stack, it's not going to exist.
I got a minute.
Yes.
Did you get my message?
Your message?
Yeah, it
Or
was
your
like
friend's
a-
message?
Oh no. It was like a honors contract.
Honors contract? I got 2 emails about honors contract.
Okay.
Really?
Okay. Actually,